right, so here's an example of axial deformation, which is indeterminate. So what we have here is this figure, and we have this load P right here, and it's supported by a structure that has a rigid bar, so BDF, so rigid bar is key, that's what we're going to draw a free body diagram of, and 3 identical aluminum rods. So we have 1, 2, and 3. They have the same elastic modulus, they have the same diameter. So here's the elastic modulus, here's the diameter, 0.625 inches. And then it tells us that dimension A, 72 inches. Those are both, so they're equally spaced. And dimension B down here, so the distance from point B to the point load is 60 inches. The lengths of all 3 rods are 90 inches, and the load is 16 kips. So let's make that red. Make this red. Well, we'll draw a free body diagram. Okay, so we're supposed to find the tension force produced in each rod. So 1, 2, 3. And the vertical deflection of the rigid bar at B. So how much does B deflect? Okay, so we know the elastic modulus of all of our bars. We know the diameter, so we can calculate the area. We know the distances. We know the applied load. We're supposed to find these 3 forces, and I'm going to change this. We're going to call this, it asks us to find the vertical deflection. So another way to write vertical deflection is V at B. In our last example, I wrote it as delta at B. It's kind of a little different. So when we think about our equation that we use for deformation, we use delta equals the force times the length all over the area times the elastic modulus. And in this case, this will be an actual deformation because it's going to be how much B moves due to that. But sometimes you'll be given a situation where it won't be, where there's actually a bar that's deforming. So there is a slight difference between a deflection and a deformation. A deformation is a change in length or angle of a material that we're looking at, or a part that we're looking at. So just to try to clarify that a little bit. Okay, so we have our solution process that we laid out. And the first step of our solution process is to draw a free body diagram and write the equilibrium equations. And usually we can solve the equilibrium equations, but this is indeterminate, which tells us that we're going to have more unknowns than we have equations. So rigid bar, BDF is what we're going to draw. So that's going to be this. So we have B, we have D, and we have F. Okay, and then at B, we have F1. At D, we have F2, and at F, we have F3. So everything about these bars is the same. The length, the area of the elastic modulus, but the force is going to change for all three, because P is over here in between B and D, so we can expect that F3 would be the smallest, and then probably F2 is going to be the largest, and F1 will be the middle force, but we'll find out. So we have, and then on our free body diagram, we should put load P, which is 16 kips, and we should label some dimensions, like that this 60 inches, and this is 72 inches, and this is 72 inches. All right, that looks like a good free body diagram. So what equilibrium equations do we have? So we have three unknowns. Some of the forces in the x doesn't do anything for us. So we have two. We can sum the forces in the y. And that equals 0, and it's going to equal F1 plus F2 plus F3, minus 16, all equals 0. So we have one equation with three unknowns, but we have another equation, so we can take a moment about anywhere. So in this situation, you can do it about anywhere, but make sure you do it about one of the points with a force so that you can end up with one equation that only has two unknowns instead of all three. So we'll sum moments about B equals 0. So we have to take F2, it's a positive moment with the right hand sign convention, times the moment arm of 72 inches. Then we have F3, it's also a positive moment, times its moment arm of 144 inches. And then we have the 16 kip load, which is a negative moment, times its moment arm of 60 inches. So we have two equations with three unknowns, so it's indeterminate to the first degree, which means we need one more equation. And so we're going to get that from our deformation relationships. So that's step 2, is what is the deformation relationships? Well, we have deformation. We have rigid bar, and we have this load on here, right? So it's probably going to deform. If it has to be rigid, maybe something like this is a good guess. So if it originally starts as this flat bar here, then we think it might end up looking something like this. And then this is going to be the deformation of bar 1. This is going to be the deformation of bar 2, and this is going to be the deformation of bar 3. Okay, so this is one of those situations where it's easier to relate because we have equal distances. So 72 inches and 72 inches. So what we know, there's a lot of ways you can do this. You can write the equation of a line, y equals mx plus b, and you'll get the same answer. You could do similar triangles, whatever you want to do, but ultimately, because 72 and 72 are equal, we can write that the deformation of bar 2 is basically the average of delta 1 and delta 2, right? So it's delta 1 plus delta 2 divided by 2. So if you did all the y equals mx plus b, set b equal to delta 1, that would be your slope-intercept. Your slope would be delta 3 minus delta 1 over the whole length. Then you could calculate it out and get the same answer if you solve for delta 2. But if you want to know more about that, please come talk to me. So we end up with an equation where delta 1, the deformation of bar 1, plus the deformation of bar 3 equals 2 times the deformation of bar 2. All right, so that's step 2. Step 3 then is the force deformation relationship. So that's the easy step where all we have to do, force deformation relationship. And ultimately what we're doing here is we're using this equation and applying it to each rod. So that's going to be that delta 1 equals the force in 1 times the length of 1 all over the area of 1 times the elastic modulus of 1. And then we have delta 2 equals the force in 2 times the length of 2 all divided by the area of 2 times the elastic modulus of 2. And lastly, the deformation in bar 3 equals the force in 3 times the length of 3 divided by the area of 3 times the elastic modulus of 3. So now we take these and substitute them in to our deformation relationship. Okay, so our next step is to substitute. So we write out that delta 1 plus delta 3 equals 2 times delta 2. And we're going to plug this in there. We're going to plug that in there. We're going to plug that in there. So this is going to give us our third equation. So it'll be that F1 times L1 divided by A1 times E1 plus F3 times L3 divided by A3 times E3 equals 2 times F2 times L2 divided by A2 times E2. Now remember that L1 equals L2 equals L3, A1 equals A2 equals A3, E1 equals E2 equals E3. So that means that we could write this. There's the beauty of doing this over video instead of in class. So I'll do this step. Is that all the L's equal? So we can pull out an L divided by AE. And then what's left is F1 plus F3 equals, then we have 2 times L divided by AE times F2. Well, we have an L over AE on one side of the equation and an L over AE on the other side of the equation, so they cancel out. That's the beauty of this problem, which makes it a lot easier to solve. So our deformation equation simplifies down to F1 plus F3 equals 2F2. So this is our deformation equation. Then we have our equilibrium equations. So we have sum of the forces, the y equals 0, and that equals F1 plus F2 plus F3 minus P. And then we have our sum of the moments about B equation equals 0 equals F2, and actually, so P was 16, plug that in. And then here I actually have this written out, so we're gonna bring this down. Paste. Okay, so what we have, so these are equilibrium equations. Okay, so all of this leaves us with 3 equations and 3 unknowns. And you can do all the algebra, that's fine, but I fully support you using your calculator to solve things, because if you know how to do that, you're less likely to make mistakes. But I will show you how to solve it by hand. But if you don't know how to use your calculator to solve system of equations, talk to me, talk to Ryan, or talk to Andrew. Okay, so we have solve, or anyone in the Learning Center can help you with this, because we all support it. So we're going to start with the sum of the forces in the y equation. But we're going to substitute in what F2 equals. So, because we have, or what F1 equals. So, what we end up with is we're going to write Oh, we're going to substitute in the F1 plus F3. Oops. F1 plus F3, which is here, equals 2F2. So we need to finish solving. So if we rewrite this as F1 plus F3 plus F2 minus 16, then we have this is here and it equals 2F2. So we can write our sum of the forces in the y equation now becomes 0 equals 2F2 plus F2 minus 16. Okay, so we get F2 equals 16 kips divided by 3. So we actually have a number. So F2 equals 5.33 kips. Alright, we have an answer. Yay! Now we need to get another answer. So we're going to use our sum of our moments about B equation. So now we know that F2 is F2 equals that. So changes to, okay, some of the moments about B, we can plug in 0 equals 5.33 kips times 72 inches plus F3 times 144 inches minus 16 times 60 inches. So now we have the F3 equals 4 kips. Okay. We have 2 of our 3 forces. Lastly, we're going to use the equation F1 plus F3 equals 2F2. So this is F1 equals 2 times F2 is 5.33 kips and then we're going to subtract F3, which was 4 kips, and we find out that F1 equals 6.67 kips. Okay, so part A is done. We found the forces in the 3 rods. Okay, so then that's part A. Now we just need the vertical deflection of rigid bar at B. And like I said, in this case, it's just going to be the deflection of that rod. If we were supposed to find the deflection here, we would have to do some more similar triangles or equation of a line math. But all we have to do here is say, so part B the deflection at B equals the deformation of bar 1. So then we can write that delta 1 equals F1 L1 over A1 E1. So that equals 6.67 kips times the length was 90 inches, all divided by 0.625 inches squared is the cross-sectional area. Oh no, that's the diameter. Sorry. 0.625, so we need to turn that into an area. So that's squared times pi over 4. Now we have an area. All times E is 10,000 KSI, which is kips per inches squared. And we get VB equals delta 1 equals 0.196 inches. And there is our final answer.